Good afternoon, everyone. I hope that you're having a great week so far and that everybody's still doing well. The lessons that I'm going to be uploading for today, which is Wednesday, and then for Friday as well, are a continuation of integration using partial fractions where we integrate rational expressions. Since none of the content on today's lesson and none of the content contained in Friday's lesson is important for your final assessment, whether you choose to follow along with these lessons or not on Wednesday and Friday is entirely up to you. Again, I'm putting them up here because I feel that I would be shortchanging people if I just ended it where we ended it on Monday. So this is part B of integration using partial fractions, and this is on page 27 of your lesson handout. When we looked at the rational expressions on Monday that we were integrating using this technique of partial fractions, there were two things that were true of all of the rational expressions. One, the degree in the numerator was less than the degree in the denominator. And if we take a look at example 3, that's the case. In the integrand in example 3, we have a quadratic polynomial in the numerator, so that's a degree 2. And then in the denominator, we have a cubic polynomial, which is degree 3. The cubic polynomial is already factored because I don't want to waste any time here factoring cubic polynomials or even larger polynomials. So that's the first criteria that needs to be true if we're going to use the technique that we learned on Monday. The second criteria is that the denominator has to be entirely factorable into all linear factors. And this denominator does factor into all linear factors. There are two unique factors, x plus 2 and x plus 3, and they're both linear. One of those factors, x plus 3, has a multiplicity of 2, and that's what sets this example aside from the examples we did on Monday. We're still going to resolve this integrand of x squared plus x minus 4 over x plus 2, x plus 3 quantity squared into partial fractions. And what you learned on Monday is still true here. If you have 3 factors in the denominator, you're going to need 3 partial fractions. So we are still going to resolve this into some number over a denominator plus some number over a different denominator plus some number over a third denominator. But what makes this unique is that we don't have 3 different denominators. One of the denominators in the partial fraction will have to contain x plus 2, otherwise we wouldn't get an x plus 2 in the denominator of our integrand. We also need a partial fraction that contains a denominator of x plus 3. The reasoning here is if you didn't have that, then you would not get an x plus 3 in the denominator. It turns out that we need a third denominator of x plus 3 squared. Rather than try to explain to you why this is the case, I'm just going to cut to the chase and give you the rule. When you have a factor in the denominator, that factor is going to contribute the same number of partial fractions to the set of partial fractions as the degree on that factor. So for example, the degree on the x plus 2 as a factor is 1, which means that the x plus 2 is only going to contribute 1 partial fraction. In this case, it's a over x plus 2. The degree on the x plus 3 as a factor in the denominator of the integrand is 2, which means it's going to contribute twice. And how that reveals itself is you end up with, in one of the partial fractions, you will have that factor to the 1, and in the second, you will have it to the 2. Just as an illustration here, if you had a rational expression that contained the following denominator factors. You had one factor which was p. It doesn't matter what p is. It could be x plus 8, it could be x minus 5, it could be x. And it was raised to the 3, and you had a second factor in the denominator let's call it q, and it was raised to the 2, then since there are 5 factors in the denominator, you would have 5 partial fractions being created when you break apart that rational expression. Some number on the top for all of these, and the different denominators would be p squared, p cubed, q, and q squared. So that factor needs to be represented each time with a degree of 1 leading up to the degree in the rational expression. So p goes from p to the 1 to p to the 2 to p to the 3. Q goes from q to the 1 to q to the 2. So that's the rule for multiplicities. Now let's worry about simplifying the equation I have in red so that we can identify the values of a, b, and c. Of course, what we're going to need to do is multiply both sides of the equation in red by the lowest common denominator, which is x plus 2 times x plus 3 squared. All right, so what I've done is I've multiplied each term in this equation by x plus 2 and x plus 3 squared. Of course, we know what's going to happen. We're going to have a whole bunch of canceling occurring. On the left-hand side, the entire denominator cancels. On the right-hand side, the x plus 2's cancel. In the term that has a, in the term that has c, both x plus 3's cancel. And in the term that has b, one of the x plus 3's cancels. And now we can write out what the new equation is without all of those denominators. We have x squared plus x minus 4 is equal to a multiplied by x plus 3, quantity squared, plus b multiplied by x plus 2, x plus 3, plus c multiplied by x plus 2. Now, in the examples we did on Monday, we were able to choose 3 different values for x to replace in the resulting equation. And one of the values of x was chosen so that b and c would disappear from the equation, which would allow us to find a. The second value of x was chosen so that a and b would disappear and we could use the resulting equation to find c. And the third value of x was chosen so that a and c would go away and we could find the value of b. The reason we were able to do that was in all of the examples on Monday, there were 3 different factors that were linear, so there were 3 different ways we could reduce factors to 0. Here there aren't. So I don't know if you remember, but in Monday's lesson, I told you at this point that I'm going to show you a shortcut. And the shortcut was to reduce those factors to 0 by strategically picking certain values of x. But I said there's a more algebraic approach that we're not going to do. This was me on Monday telling you we're not going to do this algebraic approach. Well, now we have to. And what this algebraic approach involves is expanding out everything in this equation. So I'm going to get x squared plus x minus 4 equals a multiplied by x plus 3 squared. Well, x plus 3 squared is x squared plus 6x plus 9. Don't forget, x plus 3 quantity squared means we have to take x plus 3 times x plus 3. Plus, we have b, and I need to expand out x plus 2 times x plus 3, which gives me x squared plus 5x plus 6. And then we have the c multiplied by the x plus 2. So now I'm going to expand it out entirely. I have x squared plus x minus 4 on the left-hand side. And then I'm going to multiply that a through that trinomial and get a times x squared plus a times 6x, which I'm going to write as 6ax plus a times 9. I'm going to multiply that b through the trinomial x squared plus 5x plus 6 to get bx squared plus 5bx plus 6b. And I'm also going to multiply the c through that binomial to get cx plus 2c. Now, how is this going to help us? Well, what we are going to do is look at the three different types of terms on the right-hand side and compare them to the similar types of terms on the left-hand side. What I'm talking about specifically here is we're going to look at all of the quadratic terms. And all of the quadratic terms are ax squared plus bx squared. Those are the only quadratic terms. Now on the left-hand side, we only have one quadratic term. It's 1x squared. And what that means is that 1x squared has to be equal to ax squared plus bx squared. I'm going to come back to that in a second. We also have, if I look at the left-hand side, 1x. So the linear term on the left-hand side is 1x, and the linear terms on the right-hand side are 6ax, 5bx, and cx, which means that that 1x has to be equal to 6ax plus 5bx plus cx, and I'm going to come back to that in a bit. We have a constant term on the left that's equal to -4, and on the right we have 9a, which is a constant term because it has no x's. We have 6b, which is a constant term because there are no x's. And we also have 2c, which is a constant term. And that means that that -4 has to equal 9a plus 6b plus 2c. So let's take a look right now at what the quadratic terms are telling us. The quadratic terms are telling us, and this is going to require a little bit of thought on your part, that if you take a and add b, you have to get 1. There's only one x squared. And when you look at the quadratic terms, one of them is ax squared and the other is bx squared. That means a plus b has to give you 1 because we only have 1x squared. If I do the same kind of thing with the linear terms, the linear terms have coefficients of 6a and 5b and c on the right-hand side. So if I had to add 6a multiplied by x plus 5b multiplied by x plus c multiplied by x, I would have to add those coefficients to find out how many x's I get. But when I look at the left-hand side, I can see that I only have 1x, which means the coefficients of all of the x terms on the right have to give us the coefficient of the x term on the left. When we take a look at the constant terms and what they tell us, on the right-hand side, we have 9a as a constant. We also have 6b as a constant, and we also have 2c as a constant. And when we look at the left side, the constant is -4. Now, what we have done is we have created a system of 3 linear equations. You were taught, and this goes back to grade 10 math, that if you have one unknown, all you need is one equation to find out the value of that unknown. However, you were taught in grade 10 that if you have 2 equations that have 2 unknowns, it's possible to find out the values of those unknowns. If you have 3 equations, then it's possible to find the values of 3 unknowns. So what you need to do here is solve this system of equations. Now, next year, many of you will be taking a mathematics course called linear algebra. Some of you might have already registered for that. Linear algebra is concerned with, among other things, how to solve a system of equations. So let me show you an algebraic approach to this. I'm going to label these 3 equations as equation 1, equation 2, and equation 3 to aid in my explanation. I am going to take 2 multiplied by equation 2. What that's going to give me is 12a plus 10b plus 2c equals 2. So I've simply doubled every term in equation 2. And now what I'm going to do is write down what equation 3 is. Equation 3 is 9a plus 6b plus 2c equals -4. And what I'm going to do is subtract those 2. The reason why I've done this is I've looked ahead and said that if I were to double equation 2 and subtract from it equation 3, I would get an equation with no c's. So let's see what we get when we subtract these 2 equations. 12a minus 9a is 3a. 10b minus 6b is 4b. And this is equal to 2 minus -4, which is 6. The thing I want to point out to you is what we've just done is we have gone from having a system of 3 equations with a, b, and c to a system of 2 equations with only a and b. So we have on the one hand 3a plus 4b equals -6. And we also have a plus b equals 1. You can use skills you learned in Math 10C to solve for a and b. Once you know a and b, you can put them both into some other equation in order for you to find out the value of c. All right, the reason why I keep going to a new page after just a couple of steps is my computer is really struggling lately. I ordered a new computer back in April, but it still hasn't arrived. So if I try to put too much on a page, it gets very slow and jittery. So now we are going to solve this system of equations. Probably what I would do is I would take equation 1 and I would multiply it by either 3 or 4. I'm going to multiply equation 1 by 3, by the number 3. And if I do that, 3 times a is 3a. 3 times b is 3b, 3 times 1 is 3. What this allows me to do now is I can subtract these 2 equations and eliminate the a's. And what I end up with is now I know the value of b. I have 1b equals 3, so I know b. How am I going to find a? Well, a plus b is equal to 1, so I can put 3 in for b and get a equals -2. How am I going to determine the value of c? Well, one of my previous equations was 6a plus 5b plus c equals 1. Well, I know that a is negative 2, so I can load negative 2 in for a. B is 3. C I don't know, but I'm about to discover what it is. This is equal to 1. It's now just a matter of solving this equation for C. I have negative 12 plus 15 plus C equals 1. So this gives me 3 plus C equals 1. And now I know that C has a value of negative 2. I've determined the three values A, B, and C. B is 3, A is negative 2, and so is C, negative 2. Okay, let's not forget where we came from here. We started off by looking at trying to find the integral of x squared plus x minus 4 over x plus 2, x plus 3, quantity squared. We said that that integrand could be resolved into a sum of three partial fractions, which is a over x plus 2 plus b over x plus 3 plus c over x plus 3 squared. But we determined the values of a, b, and c. A is negative 2, b is 3, c is negative 2. These are all things now we can antidifferentiate to get our answer. The antiderivative of negative 2 over x plus 2 is negative 2 ln x plus 2. The antiderivative of 3 over x plus 3 is 3 ln x plus 3. Be careful here, the antiderivative of negative 2 over x plus 3 squared is not a natural logarithm. What it actually is 2 over x plus 3. The reason for that is if you differentiate with respect to x, 2 over x plus 3, well, 2 over x plus 3 is 2 multiplied by x plus 3 to the negative 1. We can use the power rule here by swinging the negative 1 down in front, which changes the 2 to a negative. The base stays the same. We drop 1 from the exponent, and then you multiply by the derivative of what's inside, and we get, for the derivative of 2 over x plus 3, negative 2 over x plus 3 squared. Now, I've already checked this in Wolfram Alpha when I made this example up. I know what the answer should have been, and it's correct. But what we have done is figured out that the integral of x squared plus x minus 4 over x plus 2, x plus 3 squared is equal to this. In other words, this that I'm highlighting in the bottom right is the answer to the problem. And just like with all integration using partial fractions, you do not go immediately from the integral to the answer. What you have to do is break it into partial fractions first so that you can anti-differentiate it. And that is example 3. Example 4 is different than anything we've looked at. Example 4 has what we call an irreducible quadratic factor in the denominator. What does that mean? It means that we have a quadratic factor in the denominator that's not factorable. So we are still dealing with a situation here, everybody, where the degree in the numerator is smaller than the degree in the denominator. We have a quadratic polynomial, which is degree 2 in the numerator, over a cubic polynomial, which is degree 3 in the denominator. If you multiply out x minus 1 by x squared plus 2x plus 8, you will get a cubic polynomial. A degree 3 will appear in the product. Because the degree in the numerator is smaller than the degree in the denominator, we still break it into partial fractions as a first step. We focus only on the integrand, 8x squared plus 10x plus 37 over x minus 1 and then x squared plus 2x plus 8. And since we only have two factors in the denominator, we can only expect to break it into two partial fractions. The denominator of one of our partial fractions will be x minus 1, And the denominator of the other partial fraction will, of course, be the other factor of the denominator, x squared plus 2x plus 8. Now, on Monday, I told you that whenever you have a linear denominator, like x minus 1, the numerator will be a constant. What I didn't tell you is that the general rule is when you resolve into partial fractions a rational expression, each of the partial fractions will have a degree in the numerator that's 1 less than the degree in the denominator. Since x minus 1 is linear, which is a degree 1, the numerator of that partial fraction will be a constant, which is degree 0. The denominator x squared plus 2x plus 8 is degree 2, which means we have to have a degree 1 numerator in the second partial fraction. And that means the numerator is going to be bx plus c. This is what we are dealing with for the partial fractions. Again, what we're going to have to do is multiply both sides of this equation by the common denominator. Once again, I've jumped ahead here. I'm multiplying both sides of the equation by that common denominator. The purpose, of course, is to have canceling occurring. What's going to happen on the left-hand side is the entire denominator will cancel, and I will have 8x squared plus 10x plus 37 equals, the x minus 1's will cancel, so I will have a times x squared plus 2x plus 8. And the x squared plus 2x plus 8's will cancel in my final term, leaving me with bx plus c multiplied by x minus 1. Very similar approach needs to be taken in this example as the approach taken in example 3. You cannot choose values of x to eliminate a, b, and c in 3 different places. So we are going to expand this out and compare the degrees on the left with the equivalent degrees on the right. So we have 8x squared plus 10x plus 37. I'm going to cut a little corner here and just tell you that when you expand out the stuff on the right, you're going to get ax squared plus bx squared, among other things, but those will be the quadratic terms. You are also going to have, for linear terms, you're going to get 2ax. You're going to have negative bx, and you're going to have cx. These will be your 3 linear terms. And you are also going to have for your constant terms 8a minus c. So now what we're going to do is compare the x squareds on the left to the x squareds on the right. I have 8x squared on the left. Since there's an equation sign connecting the left and the right, that means I must have 8x squared on the right. The x squared on the right are found by adding ax squared plus bx squared, which means the coefficient 8 must be equal to a plus b. There is one of our equations that we're going to need to use to find a, b, and c. When I look at my linear terms on the left, I have 10x, and on the right, my linear terms are found by combining 2ax minus bx plus cx, which means if I add those coefficients together, I have to get the coefficient of the x, which is 10. My third equation is found by looking at my constant, which is 37. Well, that has to be equal to 8a minus c. And now your problem is, how can you work with these 3 equations to start eliminating some of the variables so that you can solve for the other variables? One of the things I notice, and again, I'm going to label these equations, equation 1, equation 2, and equation 3. One of the things I notice is that when I add equation 2 and 3, the c's go away. So if I add these 2 equations, I end up with 47 is equal to 10a minus b. 10 plus 37 is 47. 2a plus 8a is 10a. we have minus b, and then the c and the negative c added give you nothing. Now equation 1 is 8 equals a plus b. Well, that worked out perfectly. No, it's not always going to be this easy in post-secondary. It worked out perfectly because if I add those two equations, what I'm going to end up with is a statement telling me how I can find a. When I add those equations, I'm going to get 55 equals 11a. Okay, I know what a is. A is 5. One down, two to go. How can I find, for example, b? Well, that's pretty easy because if a plus b is 8, then I can write that 8 equals a, which is 5, plus b. Now I know b. b is 3. 2 down, 1 to go. I'm going to pick on this equation to find c solely because I still have a little bit of room on the board to write this. I'm going to have 37 equals 8 multiplied by a, which is 5, minus c. So c will be equal to 8 multiplied by 5, which is 40, minus the 37. C is going to be equal to 3. By the way, you could check something out right now. You could take a look at equation number 1, and my computer's starting to slow down already, so I'll go to a new page in a second. Is a plus b 8? Well, we said a was 5 and b was 3. 5 plus 3 is 8. That equation checks out. We could now go to equation 2. If I take 2 times a, which is 5, I get 10. If I subtract b, which is 3, I get 7. And then if I add 3, which is c, I get 10. Equation 2 checks out. If I take 8 times a and subtract c, do I get 37? Well, 8 times a is 8 times 5, which is 40, minus c, which is 3. 40 minus 3 is 37. You don't have to check this out. I'm just pointing out to you that what we now know are the values of a, b, and c, and they are correct. b has a value of 3, a has a value of 5, and c has a value of 3 as well. All right, so I'll remind you where we came from. With this example, we were asked to integrate 8x squared plus 10x plus 37 over x minus 1 multiplied by x squared plus 2x plus 8. We said that we were going to resolve or change that integrand into a number over x minus 1 plus a linear function bx plus c over x squared plus 2x plus 8. We discovered that a is 5 and b and c are both 3. By the way, if you were to add these two partial fractions together by using a common denominator and simplify the result, you're going to get back to a numerator of 8x squared plus 10x plus 37. You would never do that. I'm just trying to keep our mind focused on what we have here. We have an equivalent integral. Now, I'm going to choose to write this now as the integral of 5 over x minus 1 dx plus the integral of 3x plus 3 over x squared plus 2x plus 8 dx. The antiderivative of 5 over x minus 1 is 5 ln x minus 1. Now there are a couple of things you could do to anti-differentiate the integral 3x plus 3 over x squared plus 2x plus 8. If for that integral, let me highlight the integral so that you're absolutely clear on what it is I'm talking about. If for this integral I choose u equals what's in the denominator, so I'm just going to use this white space here to integrate that highlighted integral. If I choose u equals x squared plus 2x plus 8, that means du equals 2x plus 2 multiplied by dx. I'm going to take the 2 out and have du equals 2 multiplied by x plus 1 dx. And you actually have an x plus 1 dx in this integral, because the numerator of this integral is 3 times x plus 3, which is 3 multiplied by x plus 1. So in this integral, you have x plus 1 multiplied by dx, and that's what we have here is x plus 1 multiplied by dx. So this integral has a 3 times the x plus 1 dx, so I'm going to factor that 3 out. Then I have the integral of the x plus 1 dx, but that's 1/2 du. X plus 1 dx equals 1/2 du. And then I also have the x squared plus 2x plus 8 on the bottom, which is 1/u. We're getting there. We're almost there. We have 5 ln of x minus 1 minus 3/2 times the integral of 1/u du. I can factor that 1/2 out. Going one more step, we have 5 multiplied by the natural logarithm of x minus 1 minus 3/2. Now, what is the antiderivative of 1/u when u is the variable? Well, it's ln of u. And we're just about done. All we have to do now is remember that u, I'm just going to scroll up a little bit here for a second, that we started off by saying u is x squared plus 2x plus 8. So I can substitute that back in, and we get 5 times the natural logarithm of x minus 1 minus 3/2 times the natural logarithm of x squared plus 2x plus 8. Don't forget your plus c unless you want to lose half a mark when you do that next year. What we have learned through this entire process is the integral of 8x squared plus 10x plus 37 over x minus 1, x squared plus 2x plus 8 dx is 5 ln x minus 1 minus 3/2 ln x squared plus 2x plus 8. So this is the answer to the problem. All right, just before I polish this off, I want to point something out to you. If we were in class doing the regular version of Math 31, we would be doing this. This is an expectation in my calculus class. We would have more time to practice, obviously, but the reason why we're going to need to do it in high school is most of you are going on and taking calculus in post-secondary. I'm really doing my best here to prepare you for post-secondary. I may have mentioned this already in a previous lesson, but many of you are roughly 3 months away from going to university or some other post-secondary, and you're not going to have the support of your teachers in university, generally speaking, that you have in high school. So the more I prepare you for that experience, the easier it's going to be for you. By the way, if you were to go to Wolfram Alpha and check this out, you'll find that it is the same answer. Wolfram Alpha typically will write x minus 1 as 1 minus x. I don't want to get into why that's the case. It would just take too long. So now, when you take a look on page 35, remember section A is just practice in resolving things into partial fractions. I believe I had told you for section A there was only, I think, 1 to 6 that you could do. You now should be able to resolve all of them in part A into partial fractions. But the additional problems that you now know how to do are the ones in part B, 8 through 12. I hope you're able to follow that, and good luck if you're going to choose to practice some of these. If you need some help, get a hold of me. Have a great rest of the day, and we'll talk to you later. Take care.